about the ideal gas law, and there's one or two other ones we want to talk about. The ideal gas law describes ideal gases. So, gases that don't show forces of attraction, and gases that really, we think, don't take up any room. Now, we know that that's not necessarily true, but it describes the relationship between pressure and volume and temperature and so on if you make those assumptions. So we call it the ideal gas law. The units are very, very important inside of the ideal gas law. The gas law is PV equals nRT, where P is pressure in atmospheres, or kilopascals, or torr, just depending. You'll know it when you look at the value of the R, the constant. V is the volume, has to be in liters. N is the number of moles of gas. R is the constant, kind of like pi, and T is the temperature. Temperature has to be in Kelvin. If you look down here at the constant R, you will see that the units for this particular one are liter kilopascals per Kelvin mole. You will know what unit it has to be in based on the value of R. If you are doing atmospheres, it isn't 8.314, it's 0.0821. If you're doing torr or millimeters of mercury, it's 62.1. So you have to look and see what your units of pressure are so that you can use the right R value. I know it's kind of weird to do that, but there's a different R value for different units of pressure. We can plug in any of those four values and find the fifth. So I can give you moles and temperature and volume, and you can find pressure. That's the whole basis behind the ideal gas law. This next one is Graham's law of effusion or diffusion. Effusion is when gas escapes through a very small hole in a container. Diffusion is when gas kind of just oozes from one edge to another, kind of a thing. So like bad breath kind of oozes across a room to your nose. That's diffusion. But they both kind of work the same way. Basically what this law says, and we will practice this some in class because this gets a little dicey. Just get this down in your notes, and this equation is actually on the back of your periodic table. But the rate at which it goes is inversely proportional, meaning the heavier it is, then the slower it'll go. So the bigger the mass, the molar mass off the periodic table, the slower it'll go. And that makes sense. Who's going to go the fastest? The skinny little molecule or the big fat molecule? Skinny little molecule. So skinny little molecules go faster, big fat molecules go slower. And that's Graham's law. And we'll actually practice this a little bit in class, but I will show you how to do it as a sample right here. So how much faster is fluorine than bromine? So you will need your periodic table. Go ahead and grab that. Find the mass of fluorine and find the mass of bromine and meet me back here. Graham's law is the rate of one as compared to the other. We always want to put the faster one on top. So the problem said fluorine versus bromine. So look on the periodic table and figure out who's going to be smaller, because the smaller one goes faster. You're right, that'll be fluorine over, let's make him blue, the rate of the other guy, bromine. Now don't forget, these guys are diatomic, so it's something to remember. Is equal to, now if you look back at the equation, the molar mass of B over A, even though the rate is A over B, the reason why they're switched like that is because it's inversely proportional. So the molar mass of B here goes with the rate of B down here. And the rate of A up here belongs with the molar mass of A down there. So it's a little bit weird proportion, but it's an inverse proportion. It's just important when you set the problem up. How much does bromine weigh? Well, according to the periodic table, bromine is 79.9 grams. So 2 bromines is 2 79.9s is pretty much 2 times 80, or I'm going to go ahead and write 160 grams. Okay, I'm not really doing sig figs here, just showing you how it works. And what's fluorine? According to the periodic table, fluorine is pretty much 19 grams. So we're going to go with 2 19s is 38 grams. I am missing one thing from the equation. So look back at the equation, see if you can figure out what I'm forgetting. See how it's the square root of that? So we need to know the square root of each one, not just the mass of it. We need to know the square root. So let me go back and fix my work. I need to know the square root of this puppy right here and the square root of this puppy right here. And when I do that, I get, let's go green. I will get, what's the square root of 160? 12.6. And what's the square root of 38? That's 6.2, thereabouts. So what's 12.6 divided by 6.2? That comes in about 2.03. So the original question said, how many times faster is fluorine than bromine? So that's why we want the fastest one on top. So we say that fluorine is 2.03 times as fast as bromine is. Because if you look at the ratio, it's 2.03 to 1. So for every 1 meter per second that the bromine goes, the fluorine will be going 2.03 meters per second. Just gives us a point of comparison. I know what you're asking. How is that useful whatsoever? When in the world would you ever use Graham's law? Well, it's helpful because if you ever have a mixture of gases that you need to separate, you can do so by Graham's law. Because you know the fastest one will diffuse and come out the hole first. The slowest one will diffuse and come out the hole last. So it's a way of separating things out. If you ever did electrophoresis in biology, it's the same kind of idea. It's also helpful when you're trying to enrich uranium. Uranium comes in two flavors, 238 and 235, and we need only uranium-235 to make an atomic bomb. So how do you get rid of all the uranium-238? How do you make sure that it's the good stuff? Well, you let the isotopes turn into a gas, so we turn it into uranium hexafluoride, which is a gas, and then you let it diffuse. And as it diffuses across a tube and out of an opening, it will actually enrich, because all the slowest uranium will take the uranium-238, and all the fastest uranium will be the uranium-235. And if you repeat that process over and over again, you can take a large sample of uranium and very quickly get to the material that you want to get to. As an addendum to 11.2, I just wanted to show y'all real quick how gas laws actually make your air conditioner work. It's been such a hot summer this past summer that I know everybody had AC running, so let's see exactly how this thing works. But here's what sits outside your house. This part over here, the yellow part. This yellow part, you blow air through it, and the tubes inside of it are really, really hot. So when you blow air through it outside, hot air comes off. So you're taking heat and you're blowing it into the outside air. Then you take this fluid that's in here and you bring it over here and you bring it to an expansion valve, which is a fancy way of saying instead of being under high pressure, now it's under low pressure. And when you take that and you change the volume of it, that's what an expansion valve does. And it also changes the pressure of it. So you're going from high pressure over here in the red to low pressure over here on the right. And if you remember the law says that, Gay-Lussac's law says that if the pressure drops, so does the temperature. So the temperature drops. Now it's cold. That's why it's blue. It goes into your house. And here's where we blow cold air across this refrigerant over here. And then this travels throughout your house. And the cold gets transferred to there. Now, this line goes into a compressor. And what does a compressor do? It takes that kind of warm fluid now, and it compresses it way down under high pressure. And when you compress something under high pressure, as the pressure goes up, the temperature goes up. So, in another view of it, you see pretty much the same thing. You have this line over here. It shows the compressor compressing the liquid coming from the house. So that's a refrigerant, a gas. It's not really a liquid. It's a refrigerant, a gas, and as it gets compressed, it flows through these tubes, super, super hot. That's the fan that you blow air outside. Then it comes through, it hits the expansion valve, which opens up, allows the pressure to drop a lot. This goes into your house, which is super, super cold. And by the time air blows across it, it's not so cold anymore because you're transferring some of the heat from the house into this gas. So then the gas works itself back around to the compressor again. So really all the compressor is doing is allowing us to take heat from inside our home, hide it in this gas, get the gas to pick it up. In doing so, it cools down our house. And then outside, it jacks up the pressure, which makes it hot, way hotter than even the outside air is. It could be 99 or 100 degrees, and yet it's hotter than that. And so when the air blows across it, it will lose a lot of that heat. And then once it loses all that heat, yeah, it's hot, but it's not as hot as when it first started. And so then it winds its way back into your house. You reduce the pressure, which makes it very cold. And that's how an air conditioner works.